Welcome, everyone. I'm Reed, Director of CMSA. We're very pleased to put up this panel about math and science education and machine learning. And it's part of a program, a 2-month program we're having now about machine learning in mathematics. So we have 4 people today: Logan McCarthy, Greg Eston, Alexis Ross, and Julia Suchel. So each of them will make a 15 to 20-minute presentation, and then we'll have some discussion, including audience participation. But certainly feel free to ask questions during the presentations and after each presentation. So Logan will give us. Let's see.
Viewing okay? For those of you on the Zoom, can you hear me all right? Yeah, it looks like that's working. All right, so welcome everyone. I'm Logan McCarty, the Associate Dean for Science Undergraduate Education. It's a pleasure to be here today. And I want to focus on sort of establishing the landscape and trying to just give a glimpse of sort of where we are, what do we understand about how students are using AI and how we can help them use it better. My colleague Greg will then talk about how we can use AI to teach students. So I'm about teaching students to use AI, and Greg is going to talk about using AI to help teach students. Let me just give a little request here. I'm going to be sharing some internal unpublished data in an attempt to help encourage discussion and share up-to-date information. And I'll ask those of you here as well as on Zoom to not cite or distribute specific figures from these slides, because this is just, some of this is internal data that I wouldn't want to be shared or attributed to me in particular. So let me start with this question. Where do we stand with AI in teaching and learning today? And I think it's helpful to stand back for a minute and ask, how fast has this technology been developed for us? So let me ask the audience here. Anyone want to take a guess as to how long it took to have 50 million users of commercial aviation? How many years to get 50 million users of commercial aviation? 50, someone said 50, that's a reasonable guess. So at least US commercial aviation, 68 years. How about the internet? Sort of from the dawn of the internet era until 50 million users. Any guesses for that?
40.
Someone said 40? Well, okay, so let's call the dawn of the internet era sort of the browser era, sort of not the dawn of ARPANET. We're not going back to so yes. So then I heard someone say sort of 5 or 10 years, 7 years. If you go, let's say the first web browser, okay, to 50 million users. How about Facebook? From the launch of Facebook, Harvard undergraduate dormitory until 50 million Facebook users. 3 years. Good guess. How about generative AI from the launch of ChatGPT? How many years did it take to get 50 million users?
6 months.
Yeah, it took 5 weeks. Okay. So this is an astonishingly fast adoption of this technology. And Marta McAllister, who's one of the heads of Google Education Group, framed it this way to give some context, and I think that's helpful. In addition, so in a survey that was conducted in May of this year, about half of teachers, students, and parents are using AI chatbots either at work or at school at least once a week. So this is just a technology that everyone is using, and I think that's important context for understanding. All of our undergraduates basically are using this in some context in their life. There are obvious concerns here, and I think the most common one you hear is that we as instructors are worried about cheating, plagiarism, academic integrity concerns. I happen to serve on the Honor Council at Harvard, which is our academic integrity group. And in talking with my colleagues there, the current understanding across the US community is that this doesn't seem to have increased the rate of cheating. It's just given students a new way to cheat. I don't know if this is good or bad. It seems that students who otherwise would have found ways to cut corners using Chegg to find old problem sets or going to, in previous generations, turning to their fraternity files to get old copies of problem sets, or whatever it was, whatever method people were using to cheat. This is now just an easier way for them to cheat. It does present a particular problem because it's very hard to prove, having sat on several of these cases. If an instructor comes and says, I think that my student used ChatGPT to write this essay because the essay uses the word delve, it's very hard to prove, in fact, that ChatGPT wrote that essay simply because of particular linguistic quirks from that essay. Whereas when students were copying essays from, obscure online master's theses that they found on the internet, it was easier to prove that, oh yes, we also found the same obscure online master's thesis that you did not cite in your paper. But I think this is an opportunity for us to rethink the question of why are we assigning the assignments that we are choosing to assign. So in talking to colleagues in the humanities, who for many, many, many years would assign short assignments essentially to show that students were keeping up with the reading and thinking about what they're doing in the class, those assignments really are totally useless now because a 500-word response paper to what you just read in Pride and Prejudice is not a useful way of assessing whether students have read that. And I think we could ask the same questions about many of the problem sets that we assign, or even take-home examinations. It's not clear that those are actually going to assess students' understanding. So I want to talk a little bit about what we're doing at Harvard in terms of generative AI. And I think I'm going to frame this by saying, I think that we have an obligation to teach our students about this tool. Even a year ago, in a survey of about 12,000 students around the world, the students want to know how to use these tools. They are worried about inaccurate information. And they want to know how to use them, how we are going to help them use these tools for assessed work. So in response to this, Chris Stubbs, who was the science dean at the time, and I created a general education course that was called Rise of the Machines, Understanding and Using Generative AI. And this was last spring of 2024. I think that this was one of the first sort of college courses attempting to teach about generative AI to a broad audience. And I'll just say a little bit about this course because this was an opportunity for us to learn about how students were using this technology. We had about 78 undergraduates, 15 auditors, a range of different, yes, for those asking about the slides, I can share slides after there must be some way we can share slides easily after the talk. Most of the people who were using this were using it at least once a week, most of the students in the class. Not surprising, they're the ones who signed up to take the class. We covered sort of 4 big topic areas. There was like a section that was introduction. We talked a little bit about near-term impacts in various areas in society. We did a little bit of a technical dive. And I think it's important, even with English concentrators, to give them a glimpse of how these tools work. Because in particular, the technical design of these tools is intimately connected to many of their limitations. Why do they hallucinate? Why do they show bias? Why do they behave in the way that they do? Many of those problems are tied to the way that these tools are designed and trained. And then we talked a little bit about sort of long-term impacts. Is this going to turn the world into a paperclip apocalypse or whatever that is? So that was what we ended with, ending on a high note. The philosophical implications for the future of humanity. We asked students on the midterm paper. We asked students to try to use generative AI at each stage of the writing process and assess how effective it was. And not surprisingly, they found it was fairly effective at generating an outline or coming up with ideas. They found that it failed at actually producing, say, a 3,000-word essay. And if you've ever tried to get ChatGPT to produce long text, it tends to get repetitive and repeats and goes into bullet points and doesn't actually do a particularly good job of producing a long, coherent narrative. And this is relevant, I think, for thinking about how we might want to assign work in the future. Every week, the students were asked twice a week to make sure that they used, and the students all had access to the enterprise ChatGPT account. So they had full access to GPT-4, DALL-E, Code Interpreter, and all of the tools that they were using. We asked them to use ChatGPT each week for something not related to our class, related to something else, and to keep a diary of what they used it for. So we have thousands of diary entries throughout the course, And these were the main areas where we saw this. They found it very helpful in writing assistance. Ask for feedback with writing tasks, lots of, Python, R, coding help. Educational purposes, summarize materials, explain concepts, help with problem sets. The fact that you have, not the world's best tutor, but at least a reasonably competent tutor that you can ask questions. They found that very helpful. Brainstorming and ideation, very effective for this. And this is interesting, this is sort of an area where I think we never really had an electronic tool that could do this sort of brainstorming, interactive going back and forth idea in the past. And then finally, just replacing web searches rather than searching on Google for information, especially now that GPT-4 can search the web and find links to a reliable source. It's a useful first place to go rather than Google. I'll just mention a couple of things that we found. On the final exam, they had an hour to do these 6 ChatGPT skills, solve a homework problem for a course that they never took, create images using DALL-E, read a 30-page report, write a memo. They basically had 10 minutes to do each of these things, right? Write an outline, write and execute Python code, and do some exploratory data analysis. And I don't know if it's worth doing this here. Yeah, sure. Why don't I do this? These tools. Pull up ChatGPT. Help me analyze this data. I don't know if the folks in the audience, how much the folks in the audience use this. I think it's worth just illustrating. Sorry. So I can just take some random CSV file and say, help me analyze this data. It will load it into pandas, give me some summary statistics of the information. I'd like some hypotheses that we could test. So, for our students to see, you have sort of a research assistant who can help do, what do we want to study? Stress and sleep, occupation and sleep level. How about, let's see. How about stress and sleep? So, the fact that you can do these kinds of analyses just using free text interaction with, and it'll go and carry out the analysis, et cetera. And we asked the students to, on the exam, essentially do these kinds of analyses in real time and submit their chats, show us how they're using it. And we want them to become effective users of these tools. This was an interesting exploration because we managed to find some interesting ways that this failed. So one was we gave it a table of distances, driving distances between pairs of US cities, and we asked it to create Python code that would find the shortest route that goes from Boston, visits all the cities, and returns to Boston. A classic traveling salesman problem, which should be easily solvable, even just brute force. It's not that many cities, okay? And it came up with this was a common answer that it came up, which was 11,958 miles to visit the cities in these orders. So if you know anything about US geography, going from Boston to Houston, San Diego and San Jose, and then to Columbus and Indianapolis, then to Seattle, then to Denver, back to Boston. Makes no sense, okay? Now, what was interesting is we asked the students to carry this out and then reflect on whether this seemed like a reasonable thing. And it was interesting to see many of them, if they got an answer like this, they pushed it and they said, wait a minute, this doesn't make any sense. This can't be the right answer. But of course, if we had asked the question and we said, take these cities in China and give me a similar thing. If you don't know anything about the geography of cities in China, you would look at this table and you're like, I have no idea. It's probably correct, right? And one thing we know about these AI tools is that people tend to see it come up with an answer, especially a nice numerical answer, and it's run some Python code and done some things. It must be the correct answer. And especially if you don't have any knowledge about the subject area, you can be lulled into a false sense of security. So my colleague Greg Keston, who was helping us with this course, he created a series of pre and post test questions that we had not seen to assess the skills and concepts that we taught in the course. These were a series of questions about technical capabilities, like could you code a basic website in a half a day? Could you assess the output accuracy of AI? Could you take some data and do some statistical analysis, get some insights? Could you create data visualizations? Could you write a short Python script in an hour to do something? I'm going to leave out AI output accuracy because in a way this is not a technical skill, this is a different kind of skill. But for these technical skills, there's a pattern that you see here, which is, so in the light bar here, this is essentially people who had at least somewhat capable, felt at least somewhat capable to do these technical skills before the course. With GPT, they are now fully capable. So there's a nice take-home message here, which is basically if you know something already, even a little bit, using these tools, you can become proficient in doing these simple kinds of technical tasks. And almost everyone felt like they were somewhat proficient by the end of this. You know, they could make a simple website, even if they had no proficiency before, they could now make a simple website through these things. Yeah, question?
Is the post-test done with, like, do students have access to the generative AI tools during?
Well, so this was their self-assessed capabilities.
Oh, gotcha.
So this was, do you feel that you could do these things? On the final exam, which was these things, they actually had ChatGPT and were doing it and had to submit their chat because we wanted to see. We weren't actually interested in the answer. We were interested in seeing how they interacted with the tool and did they do that effectively. Just a few more comments here, and then I will turn over my time. What about generative AI in the broader Harvard community? A year ago, the library did a study, and there were lots of results here. I think the most interesting one was the obstacle that prevented students from choosing to use generative AI were not trusting that it's not giving, factual results. It feels like plagiarism. It undermines my learning if I do this. It's a shortcut for learning. And it doesn't cite. Now, that's changed somewhat, but you don't know where the information is coming from. And at the time, 70% said, they were asked, if we created a Harvard-sponsored AI tool, would you trust it? And 70% said, yes, this would be at least somewhat trustworthy. So this fall, we've rolled out to all Harvard faculty, staff, and researchers. So I believe probably everyone here, if you're Harvard affiliated, should now have access to this, the ChatGPT EDU. And this does give full access to the latest OpenAI models, including O1 Preview. And if you're doing, I'll say something about this in a minute. This is, for those of you who are skeptics, this is a nice environment. It's private and secure. We have a contractual agreement with OpenAI that they're not saving your data, they're not using it for training. Interestingly, as of last week, about a third of the FAS faculty have activated their Chat EDU account, but less than 10% of undergraduates have activated their accounts. We think there are two obstacles to the undergraduates adopting this. One is we had a training requirement that was a little bit clunky how they had to do it. And of course, we know that any obstacle you put, in fact, ChatGPT, interestingly, when they switched from requiring, it was free, but you had to register your account to it's free and you don't even need to register to use it. They saw a huge increase in the number of people just because the barrier of having to register an account and come up with yet another password and all that stuff, right? But also privacy concerns. It turns out that among the undergraduate population, there's a rumor that Harvard created this as a way to monitor their use of ChatGPT for academic integrity concerns, and that we are secretly, and that we wanted to lure people to use this so that we could track them for. Now, this is definitely not true, and in fact, we don't have access to this. And Harvard's policies for doing things like looking at your email and things are quite restrictive in terms of what administrators can do. But nonetheless, it's an interesting sort of social response that we're seeing to that. So this takes me to the following question. How can we create a culture that fosters responsible innovation in the use of AI for teaching and learning? And again, this is very preliminary data, but looking at this fall, large-ish courses, more than more than a third don't have any policy about AI. Fully half of the courses that are offered basically have a restrictive policy about AI, and only this tiny segment in green are essentially encouraging people. So we are stuck in a situation where a substantial number of our courses literally say, do not use generative AI in any aspect of any step of any process of any work that you're doing in this course, which is, I just want to remind everyone, completely unenforceable and ultimately probably counterproductive. Now, what about the future? So these models are improving astonishingly quickly. So Stat 110, which is one of our largest courses, it's Joe Blitzstein's theoretical probability course. GPT 3.5 basically could not solve any of the final exam problems. GPT-4, Joe did this, and of course, being a statistician, he did it 3 times independently and then had them graded independently by the TFs. They scored about 50%. And a 50% score on his final exam, it was in the 40th percentile of Harvard College students. So the GPT was scoring, better than 40% of Harvard undergraduates. But now with O1 Preview, and again, if you are doing anything in math, any multi-step reasoning, O1 Preview now, 9 months later, scored better than 95% on the first attempt. And just to give you a sense of what this is, I took a screenshot of the exam PDF, I put it into GPT-4 and said, turn this into LaTeX. I took the LaTeX, because O1 Preview doesn't do multimodal, so I can't put screenshots. I put the LaTeX into O1 Preview, asked it to create a solution, and asked it to put it all into LaTeX, and I got a beautiful document that you could use for your solution set for the course, for any classes that you happen to be teaching that maybe use math. And just to close on one lovely little thing here, in November, the very best image generators given the prompt otter on a plane using Wi-Fi produced otters, kind of something that maybe looks like a plane. And 21 months later, we have this for otter on a plane using Wi-Fi. And just to give a sense of the change here, now it understands when you say an otter on a plane, we don't mean literally an otter sitting on a plane, we mean an otter on a plane. And I think it's worth keeping that in mind when we think about what's happening here. So a couple quick takeaways, and I will turn over to the next speaker. Unless there are questions, I don't know what the typical practice is here. Want to do some questions now or questions later once we're all assembled? Yeah, Sonia.
So given the 95%, and I'm curious if you ran the cities through the new 0.1 version and what it gives. But
You're curious if I ran what through the
no, the problem you gave last semester of giving the salesman's problem.
Oh, I'm sure it would get this traveling salesman problem correct. O1 Preview, yeah.
Anyway, my question is, how should we teach, right? We are in the science. Because clearly, yes.
Yeah, so I think this is sort of the challenge that we face as educators. I've talked a lot with Jeff Lichtman, who's our new science dean, about this. And he feels like, so number one, we have a current structure of STEM education where we teach a lot of introductory material, sort of in the hopes that some of it might be useful someday for something that you want to do in the future, right? Am I going to need linear algebra? I don't know. They make me take linear algebra. Maybe I'll need it. I don't know. Okay. Am I going to need? He always brings up organic chemistry, which is painful to me because that's a subject that I teach. He's like, I had to go to medical school. They made me take organic chemistry. Why did I have to take organic chemistry? Right. But then he says, and they made me take physics and optics. And in fact, he now spends his life doing optics because he is a microscopist, right? So it turned out that for him, optics happened to hit something that was useful. He did admit that later on he had to completely relearn optics because he didn't remember anything from. But I think the key thing here is we now have tools that certainly for any factual information can tell you what you need to know and probably can help you learn almost any skill that you might eventually need to know. So what are the things that we need students to understand? And he feels like we need to actually invert our education and start with what are the compelling, challenging problems in the world within science that we need to try to solve. And then try to explore almost more like a tutorial model. Like, okay, we really want to try to solve the physiological basis of mental illness. That's a big, hard, unsolved problem. We don't even know if we have the right approaches to thinking about that problem. Well, what do we need to know if we want to attack that problem? Well, maybe we need to know something about physiology. Well, if I want to know about physiology, maybe I need to know something about microscopy. Well, if I know about microscopy, I need to know about optics. And then you let that serve as a motivation for what you want to do. Because then it's about, because these tools are very good at answering questions. Then it's about what questions are we asking. So that might be a motivation, but I think this is like a crucial question for us to ask, because yes, it's not going to be long before any you know, even research grade math questions, these are gonna, you know, Terry Tao had a fascinating, you know, response to playing with this O1 preview. And I think those questions are really gonna be profound. Because it's not gonna be, you know, here, go prove this theorem. It's what theorem are you asking it to try to prove? Right? Now you can ask it, like, what theorem should I prove? I don't know, is that helpful? But yes, I think this is, you've hit on exactly the right question here. Other questions we want?
Well, that'll be a good one to pick up.
For the
Yes, with
discussion,
the whole
yeah.
panel, but maybe we should move on to the grade.
Sure.
Thank you.
It's always a danger when you're talking about some AI technology and then you have to get technology working. Okay. So as Logan said, I'm going to talk a little bit about how we could use generative AI to best teach our students. So I'm Greg Keston. I'm a lecturer in physics and associate director of science education, and I'll talk sort of about the principles we should use in creating activities to teach students. I just want to say that some of this work has been done with these colleagues here. We have a preprint, Father Kelly Miller and class and Gregorio Ponti. So I'll give a little outline of what I'll talk about. So first, I'll talk a little bit about where does AI fit when we're thinking about it in terms of how an instructor is going to use it. And then I'll talk about some challenges in STEM, which helps focus one use that I'll talk about. And then I'll show you a system and how we apply some best practices in science education to help solve these challenges. And then I'll show you this randomized controlled experiment that we did in a large intro physics class and give you the design and then show you the results. And feel free, if there are questions, I'm perfectly comfortable if people want to interrupt at any point and ask a question. You know, as instructors, where is best to employ generative AI? Because there are many different places that you can employ it. You can imagine when you're first introducing students to concepts, right? In the lecture or in the pre-reading, maybe you have the students, you know, start learning the material with the AI. Maybe in section, they're guided, they help the TF in a way to guide the students. You can imagine there could be homework hints from an AI. In lab, you could use AI vision to help observe things that maybe the students don't know they should observe something, maybe that's subtle. Studying, right? We give the students, at least I give the students a couple practice exams. I wish I could give them more practice exams. Why not have something generate practice problems for the students? And even in exams, right? We give the students calculators now. Why are they not the calculators on exams? And so the question is, where should we put generative AI? And the answer is all of these eventually. My colleague, Dr. McCarty, he employed these to great effect in his class in many of these. But if you're using, if it's a class that's sort of a standard large science class, it can be actually dangerous to just, you know, use AI as a sledgehammer. Some early work on just giving students ChatGPT to learn. If you do post tests after the students learn with, say, ChatGPT, the students do worse on those tests because they're using it to get the answers. They're just circumventing critical thinking. So, and the reason why is because, you know, these AI systems, one way they're trained is this reinforcement learning from human feedback, which I imagine, you know, if you give a lot of very useful information as an AI, then the humans say, oh, I like all that good information, but often that's the answer, the thing that the student should think through. So what I and my colleagues thought was, well, it's generative AI. Let's let it be generative. let's not worry too much about it giving an answer, say, on a homework problem. And so we'll just employ it in the beginning, when students are just learning. It can generate a bunch of the initial content and the students can interact with it that way. And another reason why this is good is because there are challenges with the pedagogy to introduce students to material without AI. So in a science class, STEM class, how do you usually introduce students to material? What are your options here? So one option is just sort of the traditional classroom where, you know, the students are learning the material pretty much in the class, in the lecture. Maybe they'll do a little bit of reading beforehand, but like the first substantial sense making of the material, working through problems is in the classroom, then they go home and then they do homework. But if they're learning it all together in a classroom, then you have these problems, right? The students are working at the same pace, pretty much the pace of the instructor. The feedback is not individualized to every single student. They may have a question and they just can't go off and think about it. And because of these first two, you also can get low engagement from the students. And active learning does help. You can have an active classroom where you get a little bit of individualized feedback from, say, peer instruction. And you could get some more pacing on their own working in those groups, but still, this one size fits all, just has some problems, which, you know, we all, you know, if you look at comments from students after classes, like if they say class was too fast, next student says class was too slow, right? So you can't win. So why not try to introduce material in the flipped classroom model, where students learn the material before class, they start doing problems, maybe some activities, various quizzes, videos, things like that, learning before class. And then when they get to class, they can do sort of the higher level thinking, sort of learning how to do things with projects, do applications, things like that. But this also has been found to show some problems, which is, again, students have low engagement. They're just sitting alone. They have no guidance and support. Maybe they're told to go through something, but if they have a question and they're not sure, like the answer isn't in that material they were giving, it's not dynamic. It can't just respond to this question the student has, or every question that every student has, really. So that also is a problem. So the idea that we had was, all right, let's use AI to give students individualized feedback and let them go at their own pace. And so in doing so, we wanted to make sure that we were following some well-established principles in science education, which is we want to make sure that the students are actively engaged. It's been shown a number of times that active learning is better than passive learning. So we want to make sure the students remain active. We want to make sure that they have a growth mindset. They can really do this. And we also want to make sure that the students aren't cognitively overloaded. We aren't giving them too much material, because not only could this be giving the students the answer, but it could also just give them way too much material to think about. So just to give you an example of what that looks like. So this is the system that we're using. So basically we have a question that a student's working on, and then they'll ask the question, say, help me get started. And then the AI will answer the question. So this is a question, it's about two astronauts in space and they push off each other, and it's asking about the momentum of the system. And so it just goes and solves it, right? It just gives a bunch of information. And this is sort of the default behavior of ChatGPT, because this is just the only instructions that the AI has here is, you're a physics tutor, you're helping the student with that question. And so, you know, the students get overloaded by a lot of material, gives them the answer, not how we would teach them properly in an ideal tutoring situation. But if instead you tell the tutor, the AI tutor, say, you're a physics tutor, but like guide the students, like encourage critical thinking. You know, you can do this. Tell the students they can do this. And then also just be brief. Don't give the students too much. And then the exact same question and the exact same input from the student, help me get started, gets the AI to respond in a way much more like how we would interact with a student. It says, yeah, okay, let's think about this. Like, are you familiar with momentum? What do you know about Newton's third law? And then it has this back and forth where it seems like they are engaging, they're not overloaded. And so this will give you a sort of a sense of what it looks like, what the students, sort of a basic look at what the students were seeing. Maybe I should pause. So I'm going to talk about the experiment, but I'll pause in case anybody wants to interrupt. Okay. All right, so so the experiment that we did was we basically took this class. It was a large introductory physics class for students in the life sciences, and randomized half of them into an active learning lesson, and the other half did this AI supported lesson. And I'll break down what that means. So the way that the active learning works, so these transformed lessons, thanks to Logan McCarty, basically implemented these transformed lessons into the classroom. So they're not passive lecture, but they're active learning where the classes consist of a few activities, maybe 4 or 5 activities, and the instructor introduces each activity. Students do peer instruction, they work with each other in groups, and the instructor walks around, talks to them, see how they're doing, what's the pace they're going at, what do they need help with, and then after several minutes, the instructor gives feedback. And this has been shown to be much more effective than just passive lectures. And so that's what the one group does. We've been teaching like this for several years here in this classroom. And that group who experienced the lesson, let's say it's on fluid dynamics, they had a pre-test on fluid dynamics and a post-test on fluid dynamics. And then group 2 also had same pre-test and post-test, except instead of the students being introduced in person, they were introduced just in that same system through a video. Exact same introduction, just video, same instructor. And then the group activity with peers and the feedback was done with this AI. So the AI was had the prompt that you saw, which is basically having it act like a well-seasoned instructor, but it also has some information about what the problem is, what the solution looks like, and it essentially has knowledge of what the instructor feedback looks like in the in-person version of that activity. And just to give a little information on how it's controlled, it was the exact same content and handout. So they had a handout they were working on while they were asking these questions to the AI. Each group was around 100, they were randomly assigned, and the tutor was PS2 PAL, physical sciences 2. It's a class, PAL. And then I just want one last note on the study design, which is, so this is sort of a condensed version of what you saw pre-test, post-test, and the 2 conditions. But we did that twice, once with surface tension and one with fluid flow, and each group got to experience both conditions. And doing this allowed us to analyze it in a way where we could control variables that weren't of interest. For example, if one group just happened to be have more background in fluid flow or something like that. There's some, so that was helpful. Okay, what did we find? You're wondering? So this is the score on the post-test and the score on the pre-test. These are the means. And so you can see that the score on the pre-test for this is everyone together on average was around 2.7, and then after the active lecture it was over 3.5, almost a whole problem better, and then the AI did even about a problem better than that. So significantly more learning, it seems, from that AI lesson. And so, but did they like it? We took their friends away, right? So did they? And so okay. So here's the students' perceptions. So we asked them, how engaged did you feel? So these are self-reported. the students said in the AI group that they felt, I mean, they both felt engaged, but they felt a bit more engaged in the AI condition. When you're working on a hard problem, are you very motivated to keep working on that? And the AI group was slightly higher there too, so more engaged and more motivated. And as far as enjoyment and growth mindset, can you actually do this, learn this material if you work hard enough? Those were about the same between the two groups. And the enjoyment, this was, so I'm giving the mean here, but it's sort of split. There were some students who were worried, they were going to, that all their time is going to be with the AI. But, and there were some students who really loved it, loved their individualized, but on average, it was about the same. Yeah.
When you did the AI people, were they in the room with their computers using AI next to each other, or were they in the dorms?
They were at home and we were on Zoom, at least to get them started. And the reason why is actually a wonderful segue to the next slide, which is the time on task. Because some of the students had classes after the 75 minutes of that class. And we expected some of the students might want more than the class time to do it. So we let them do it at home. We asked, try to do it in one sitting, but if you can't, you have a class, then just come back to it. So this is how much time the students spent with the AI, and the dotted line is 60 minutes. That was the in-class lesson. And the thing to notice here is that, it's a big distribution. There's a good amount of students who, wanted, much more than class time. There are, a lot of students who wanted to do less than class time. They could do it faster. And the students who said lecture's too fast, they actually did take more time. That's it's helpful to see that. Also, the median time, and you can imagine when they're in the classroom, if they work on the problem and then I go and give the feedback, give them the answer, some of that time's wasted. Some of them got those answers. So some of them will have wasted time. So you'd expect that if the students were really working through at a good pace on this without that wasted time from my repeated feedback, they on average, or the median time would be less. And so here the median time's around 49.50 for the AI group. So they saved a bit of time on the median. Yeah.
For the students on the tail end of this distribution, did you see like greater gains from using the AI tutor? So I guess I would expect that there are more gains for those students.
Good question. So there's no correlation with time on task and the post-test score. And the reason why I would guess, and this has been seen in other experiments, is that the students who just needed more time took it, took more time. I see what you're saying for gain, would they see more gain?
Yeah. If they can now go at their own.
If they can now go at their own pace, we didn't see a greater gain. It's a good point. Okay, so that's all. They learned a bit more. They were engaged, and it took median less time. So sort of the takeaway is, should we just introduce students to material in this way with AI that's a bit more dynamic? And then when we're in class with the students, we can do projects with them. We can do harder problems, things that might be more similar to an exam. Things like that, which might be more dynamic, more personalized. Yeah.
Yeah, just a quick question. So remind me, is the AI sort of modeling group dynamic, or is it more like a one-on-one conversation?
So it interacts with them as a tutor. So it
like a private tutor.
Like a private tutor, yeah. So it it would not, for example, pretend it doesn't know something, but it might say, well, think about this. So it isn't exactly mimicking a peer.
Well, and it has the tutor sorts of tactics, and I imagine maybe it's a little different in a typical university. There's going to be a lot of confusion introduced in groups also, because some students just aren't getting it. And this probably has, do you have a sense of how to measure the confusion in group setting versus what you can avoid in that? I recognize it might be hard to
Yeah, I mean, so the way that these activities are typically done is the students aren't actually asked to complete the activity. It's more that they're meant to be primed. So most of the students don't actually even finish them. It's so the feedback can be more effective. So in that way, if confusions are introduced, they're solved then with the feedback.
This is a really cool study. I imagine that like one of the things that could influence students being more engaged with the AI tutor is just like the novelty, like, you know, generative AI in a class, that's really exciting. And I'm curious, do you have any sense of how much that contributed to the learning gains, and like maybe one way to see if that is the contributing factor is would the gains go down if you did it?
Yeah, no, this is a really good question. So it turns out that the post-test score for the AI group didn't correlate with the amount of use of AI beforehand. But the use of say ChatGPT did it anti-correlated with how well they did on the post-test for the in-person group. So you can imagine, this is my best guess at what was happening here, is that the students who are outside of class circumventing their critical thinking using the default ChatGPT behavior are, for some reason, not learning as well in the classroom. But as far as the AI group, there wasn't that correlation. Should we?
Does the AI as a tutor ever introduce confusion?
It may.
Measuring.
So we did not see it giving too many incorrect answers because we gave it the correct answer. So we essentially worked to anticipate what the students would ask, and we gave essentially the feedback that we would have given that student to the AI. And luckily, this class has been taught. I mean, I've been working with Logan in this class for, I don't know how long Logan's been doing it, but my work is built on his work in the class. And so the feedback that we give in the class builds every year, thinking about, oh, what were the students worried about? Let's change it in this way or that way. And so in that sense, what we gave to the AI was very curated based on what you would expect a student to ask. So there weren't a lot of questions out of left field, and giving it the answer made it so that it was pretty accurate. Should we move on to our?
You have a question?
Oh, there's a question in Zoom. Any practical steps to take in integrating generative AI? Sure. Any practical steps to take? I'm not sure exactly what this question's asking, but I will just say a word about how we're integrating it now. So now what we had as pre-readings in the class are converted into these sort of activities where the students are asking questions. Some of them were videos where the students can now ask questions on them. And even pieces that were in the lecture were now like basic introduction of material are being moved into that pre-class and using more advanced material for the lesson more.
Thank you.
Give me 1 second. Okay. Cool. So hi everyone, my name is Alexis Ross. I'm a PhD student at MIT CSO. I'm really excited to be here. I work on AI for education, and today I'm going to be talking about some of my work on using large language models to teach adaptively towards different students' misconceptions. So I think Greg and Logan really motivated why generative AI in education is exciting, but just to really drive the point home, There have been a ton of headlines recently about the transformative power of AI, generative AI, will chatbots teach your children, every student will have a personalized tutor. And I think that amidst this hype, there is really something genuine to be excited about. And in particular, there's this sort of famous study from a few decades ago called Bloom's 2 sigma problem, showing that a student who received tutoring performed on average 2 standard deviations better than a student who learned in a classroom setting. And of course, scaling up one-on-one human student tutoring is really, really hard. And so can we use generative AI to achieve some of this dream? So what makes a good tutor? I think Greg talked about some of the aspects in his talk, but just to lay out some answers here, and I'm taking these from Google DeepMind's recent Learn LM report. One of the key things that a good tutor does is stimulate a student's interest and motivate them. A good tutor also encourages active learning, so you want to ask questions that require active engagement. Good tutor will deepen metacognition, so you don't want to give away answers too quickly, you want to ask questions where it's appropriate. And also a good tutor is going to be adaptive. So infer student beliefs, provide informative explanations that are tailored to the student. And what I want to highlight is that even the aspects here that aren't explicitly about adaptivity require adaptivity. So in order to motivate students, you need to understand what motivates them and be adaptive in that way. So I'm going to focus on adaptivity here. That is not to say the other things aren't equally as important, but that's just the focus of what I'll talk about. And so, okay, I'm going to motivate the topic a little bit more. So I want you to imagine that you were teaching fraction arithmetic. So maybe you're tutoring, I don't know, a family member or something like that. You might start by first probing the student's understanding topic. So maybe you'd ask, what's 1/5 times 2/5? And let's say the student said 2/5, so they got this question wrong. Does anyone have any guesses for what the student might be doing here? Yes.
Maybe they're
Yeah, Logan.
multiplying the numerators. And
Yeah.
They're doing it like addition.
Exactly.
Multiply the numerators, there's a common denominator. Keep the denominator.
Exactly, yes. So exactly, you might immediately develop this hypothesis that they seem to be overgeneralizing the addition procedure. So only applying the operation to the numerators. And this is like a quite common misconception that students learning fraction arithmetic have been shown to have. Now you might try to validate this hypothesis. So maybe you'd ask, what's 1/4 plus 1/8? And the student says correctly 3/8. This seems to support the current working hypothesis. Now let's say another student got this first question correct. So what 1/5 times 2/5 is 2/25, but said that the second problem said 2/12 for the second problem. Well, it seems like this student might be overgeneralizing the procedure for multiplication, so applying the operation to both the numerator and denominator, which you're not supposed to do for multiplication. What I want to highlight is that you probably teach these two students quite differently. So the addition generalizer would probably benefit from additional practice with multiplication problems, maybe particularly ones with equal numerators. And then the second type of student would probably benefit from addition problems. So key idea here is that adaptivity is at the core of good teaching, and it requires inferring student beliefs and any misconceptions, and then selecting the most informative teaching material based on those beliefs. So the questions that we're asking in this talk are, can large language models like GPT-4, as well as other automated teaching methods, do this? So can they infer student misconceptions, and then can they select personalized practice problems based on these misconceptions? So I'll talk about a recent paper with my advisor, Jacob Andreas, and the title is Toward In-Context Teaching, Adapting Examples to Student Misconceptions. Okay, so what we do in this work is we formalize this notion of adaptive teaching, and we introduce an evaluation framework called ADAPT that allows us to test different teachers' adaptive teaching abilities. And I will talk sort of at a high level about all of this, but in the paper, there's more details on the formalization and things like that. But the key idea here is ADAPT places a teacher in conversation with a student. And so the student has some misconception that's unknown to the teacher. And the teacher is tasked with selecting examples for teaching some target concept. So in the case of fraction arithmetic, the teacher is interacting with a student, but they don't know if the student is an addition generalizer or a multiplication generalizer. And the teacher would start by first selecting a practice problem, The student would make a prediction, and then the teacher would provide the answer, and this process would repeat. And at the end of the teaching interaction, a teacher would be measured by looking at how efficiently the students learned under that teacher. So a good adaptive teacher should lead students to learn more effectively. And so we introduced, so the evaluation framework that we introduced has 3 domains. So there's the fraction domain with these 2 types of student misconceptions. There's a verbs domain, which I'm not going to go into detail here on, but the task here is to try to categorize these English verb lemmas based on how they work in past tense. And then the 3rd domain is this function learning domain, where the student is trying to learn how some function log operates. So I'm going to return to that last function domain at the end of the talk and talk a bit more about what that looks like. But ADAPT allows for evaluation with both human and simulated students. And the nice thing about the simulated students, where here these students are modeled as doing Bayesian learning, is that you can run experiments at scale and sort of directly measure how efficiently the students are learning by looking at their posterior beliefs. Okay, so that's a bit about the evaluation framework. And now I'm going to touch on the different teachers that we evaluate. So we evaluate GPT-4 as a teacher, and we do so by prompting it. And we say, you're a GPT teacher, an expert teacher. Your goal is to teach a student how to multiply and add fractions as efficiently as possible with input and helpful examples. And you'll be interacting with a student who has spent some time with fraction arithmetic and has some misconceptions about how it works. And then we spell out the space of misconceptions that the student might have. So we say, there are students who tend to incorrectly multiply only the numerators when multiplying fractions, and analogously for the other type of student. There's more information in the prompt not shown here about the details. So here's what a teaching interaction would look like with GPT-4. So GPT-4 would select a teaching problem, a fraction arithmetic problem, what's 1/2 plus 1/4. The student would give their prediction, and then it would continue. And then at the end of the interaction, we ask GPT-4, based on this interaction, what kind of student do you think I was at the start of this session? So this is how we elicit the language model's beliefs about the student misconceptions. So that is the GPT-4 method. And then the second teacher that we evaluate is something called ADAM, which stands for Adaptive Teaching Towards Misconception. So this is a new probabilistic teaching method that we introduced. And again, I'm not going to go into details here. Didn't want to throw math on this slide, but details are in the paper about how exactly it works. But it has 2 key parts. The first part is one that infers the parameters of the student's prior belief, so the distribution over the concept space for the Bayesian students, based on the predictions that the teacher sees throughout the teaching interaction. And then the second part is based on these inferred prior beliefs, Adam selects teaching examples that would maximize the student's new belief in the true target concept, so like the true procedure for doing fraction arithmetic. And we compare these 2 teachers with a range of baselines. Won't go into detail here, but for example, the random teaching baseline just randomly selects an order to show teaching methods in. So what do the results with simulated students look like? Again, the thing we're interested in is how efficiently can teachers get students to learn? And so what we're interested in is the student's learning curve. And so if you plotted, the student's belief in the target concept as a function of the number of teaching examples that the teacher has shown them, we're interested in the area under that curve. And when you look at these AUC values, so here shown here are AUC values for some of the learner types for the student types that we evaluate. And we see that, can you see my mouse? Okay, yes. We see that GPT-4 is sometimes outperforming the naive random and ranking baselines and sometimes not, but that Adam is consistently outperforming all baselines across for all of these students. And we can also ask, if these teachers made the correct inference about the student misconception, how well could they have done? So this is sort of an upper bound analysis. And we see that for all teachers, as expected, when you just tell the teacher the misconception, the student misconception, it doesn't have to do this guessing about student misconception, performance is higher. So for example, GPT-4, when it knows the student type, performs better than when it has to guess student type. But notably, we see that Adam, despite not knowing the student type and having to maintain that guess, is performing on par with this non-adaptive sort of upper bound teacher that knows the student type. Okay. Then we run sort of similar experiments with human students, and I think this is quite interesting. So again, we run experiments with human students for this function domain. And the concept here is you have some function WUG, it takes in a number, an input number X, and then it returns something. And that something, that output is either undefined or another number. And so WUG of X has this form. If some Boolean function f is true, then WUG of X is undefined, and otherwise it computes a linear function for some values of A and B. And in this domain, there are two types of students. There's an F learner who has a misconception about when WUG of X is undefined. So it's a misconception about the Boolean f function. And there's a B learner. So the B learner has a misconception about the value of B, but knows the correct Boolean f. So what we do is we recruit human, yes.
Do they know the form?
Yes, great question.
So they know what's in that little box.
Yeah, they know that it has a form like this.
They don't know what the Boolean is.
Exactly, yeah. And there's like a drop-down menu. I'll show you in the interface where, yeah, there are options. Great question. Yeah, so we recruit students on Prolific, and we tell them you're tasked with learning how this mystery machine works. So we tell the student that they have 10 minutes to interact with the teacher in a chat interface. This is what it looks like. So they can chat with the teacher on the left, and there are places for them to make guesses on the right. The students are given hints by some Dr. Smith that determine their misconceptions. And so, for example, shown in the top right, this is like an example of a hint that Dr. Smith would give. So it's a hint about the Boolean f, so when it's undefined, and also what the values of A and B are, and one of these is wrong. So that's how we create these misconceptions. And we tell students that their bonus at the end of the study depends on how efficiently they can figure out how WUG operates. And so they're incentivized to enter a guess in the sidebar as soon as they think they know what WUG of X does. And so to your question, Mogan, here, there would be like, there are drop-down options, and they're also told at the start of the study what those options are. So we can look at a similar metric that we did for the simulated students, like how efficiently do students learn under these different teachers? And here is a bar plot showing that similar AUC-like metric. And what we see is that both GPT-4 and Adam outperform the random teaching method. And this is a statistically significant method. So these teachers seem to be doing something non-trivial pedagogically, even for human students. But interestingly, when you look at the inferences that the teachers make about the students' misconceptions, GPT-4 is much worse than Adam. So in particular, it's at about 50% accuracy, which is random chance, while Adam is making inferences that are around 80% accurate. And this is sort of interesting and less surprising to us because Adam is making some pretty strong assumptions about the way students learn. It's making Bayesian assumptions, but these seem to have non-trivial predictive power even for human students. And these side-by-side results kind of raise an interesting question, which is, if Adam is making much more accurate inferences than GPT-4, why are they both outperforming random chance or the random teaching method, and why are they performing comparably? And I'll return to that in like 2 minutes. But using this framework, we run a couple of analyses of what the teaching methods seem to be doing. And so the first analysis is what we call selection of critical examples. So remember that WUG has this structure where it's undefined if some Boolean function is true. Let's say that true Boolean function was greater than 2. So WUG of X is undefined when X is greater than 2. And let's say a student thought that it was actually when it was greater than 4. So this is incorrectly, but a spuriously incorrect belief, because in particular, there are only 2 examples where the student will realize that they have this incorrect belief, because for all other examples, these two concepts are going to agree. And so the teacher, like a good teacher, should select these two examples early on in teaching in order to correct the student's misconception. And so here's a plot showing when each of these different teachers selected one of these critical examples throughout teaching. So the x-axis is showing basically when in teaching that example was selected, and each square corresponds to a critical example being selected in some random trial. And what we see is that all probabilistic methods, including Adams, select critical examples early, even when they don't know the student type. So this is because they're able to infer the student misconception. And we also see here that Adam performs comparably to the non-adaptive teacher when the non-adaptive teacher knows the student misconception. And interestingly, when GPT-4 knows the student misconception, so that's this row here, it selects critical examples early, but still later than the other methods. And there is a delay in when these critical examples are selected when GPT-4 does not know the student misconception and has to make this inference. So this altogether seems to suggest that a language model like GPT-4 seems to have some non-trivial adaptive teaching abilities because these examples are concentrated early, but that maybe it's not as good at making these explicit inferences as some of these more structured teaching methods. Okay, and the last analysis I'm going to talk about is we look at some qualitative differences. We try to understand how is GPT-4 versus Adam teaching mathematical concepts. And so what we look at here is when log of x is defined, the student is trying to figure out what the values of a and b are. So they're trying to learn the slope and bias. And we look at what examples x are selected by these different teachers to teach these concepts. So again, I'm going to ask the audience, do you have any, how would you teach if you just had to select XY pairs to teach someone the weights of a line? What examples might you start with?
0.
Okay, 0, right. And that's because it's very informative. It tells you the bias directly. Okay, great. And after that, you might select maybe smaller values of x because maybe someone doesn't want to do large math arithmetic in their head. So it's hard to, yes. Yes, 1, maybe 1, maybe -1. Okay, thank you. So that's exactly what we see GPT-4 do here. And so it's selecting examples starting at the origin. So what's shown here is the x-axis is the order of the data point. And then the y-axis is the value of x. And we see that there's this concentration that it's selecting examples close to the origin at the start of teaching and then sort of fanning outward and moving and selecting inputs in order of increasing magnitude. So it seems to recover this sort of intuitive idea about how you might want to teach mathematical concepts. And this seems to suggest that a language model like GPT-4 has encoded its information that inputs closer to the origin are easier to learn from than those further from the origin. And what I think is really exciting and I want to highlight is that an idea like this is really hard to represent in a structured model, right? It's like, you can express that in language, but it's quite hard to express that in some sort of probabilistic hypothesis space. And so I think this is where there's a lot of potential for leveraging large language models. And in contrast, this is how Adam selects teaching examples. So it starts with higher magnitude examples and then selects examples in increasing order. And this is the result of the way that the hypothesis space for Adam is constructed. Happy to talk about the details of why it has this particular shape offline. But again, yeah, what I want to highlight is there seem to be complementary advantages of methods like GPT-4 and Adam. And I think what's really exciting is to think about how we might combine them to achieve better adaptive teaching. So I will end on that note. And what we found really quickly is that GPT-4 can adaptively select teaching examples better than naive baselines, but it struggles with explicitly identifying student beliefs. And maybe by explicitly modeling student knowledge with Adam, we can improve teacher efficacy. We saw that in the experiments in this paper. And so the key takeaway I want to leave you with is that maybe we can combine the flexibility of LLMs with the precise inferences enabled by more structured modeling approaches like ADAM to achieve better adaptivity towards misconceptions. That's all. Yes.
It seems like in Adam, you needed to have some finite set of beliefs that the students conceivably could have.
Yeah.
But when I come to my office, that set does not seem finite.
Yes, absolutely. Okay, this is a great question. So for the purposes of this study, we were trying to do this sort of controlled experimentation to see if you assume that there is a space, how do you, can language models uncover them? But you're exactly right. I think that, and one of the things I'm really excited about is actually using language models to try to uncover that space of misconceptions. And so I'm working on some follow-up work, trying to see whether you can use language models to identify that. Is there like I guess the question is there a low dimensional space of misconceptions that you can recover by using language models to like generate hypotheses about what students might be confused about? And we're exploring that in the context of like coding education. But great question. Okay, thank you.
Very.
Okay, perfect. I get to round off our panel series of talks here today. So what I'll try to do is tie together some of the threads from the previous talks. And be a little sort of like forward-facing, future-facing with, you know, aspirationally, what can we expect from AI tutors and AI systems going forward? How do we get there? What can we do? So I'm Ilya Sokolutsky. I recently started as a faculty fellow assistant professor at NYU. A lot of this work, most of this work was done at Princeton. I joined NYU like 3 weeks ago, so Princeton is still up here, but you know, you won't find me there anymore. So I think what I'll talk about today to tie those themes together is why I think machines should have human-like representations, why in general it's useful for us to have human-like machines, and how that ties into this idea of having student-centric or personalized AI tutors in the future. So to motivate that, let's start with a little bit of an analogy. On the left here, we have Basil Valentine's table of alchemical symbols, right? These chemical characters from the 15th or 16th century. And on the right, we obviously have a modern day periodic table. So imagine a meeting between Basil, the 16th century alchemist, and a 21st century chemist, right? They live in the same world. They're intimately familiar with the materials found in this world, and they study those materials. They try to understand how the world works. But in a conversation between them or in experiments that they're jointly running, they're going to have significant difficulty expressing their values, their beliefs, and generalizing the results of an experiment that they run together. The alchemist would likely learn. Yeah, we'll share the slides afterwards for anyone who wants them. The alchemist is likely going to learn poorly from examples of a reaction demonstrated by the chemist due to not having the right inductive biases for how the world actually works, to our, you know, modern day understanding at least. So what we typically say, and this is a little cartoon of what we say, is that the alchemist and the chemist lack representational alignment, right? They represent the world in fundamentally different ways, and this impedes communication, generalization, and learning. Now, that's not to say that two modern day chemists are going to be completely aligned, that they're going to completely agree in every aspect of the representation of the world, but they likely will be much more aligned in how they represent the world, and they're going to have an easier time communicating and working together. So what I want to talk about today is how we can quantify that notion of representational alignment and why it matters. All right. So this is a schematic of the simplest possible method for studying representational alignment. Suppose that you have some set of data and you'd like to figure out how two intelligent agents, maybe they're humans, maybe they're machines, we don't know, we'll call them Alice and Bob, how aligned they are in their representations of those objects. Turns out that all we need to do in order to figure that out is to ask Alice and Bob to give us similarity judgments or distances between those pairs of objects. Right, so I can ask Alice, how far apart or how similar are the chimp and the eagle pictures? How similar are the chimp and the lemur? I can compose this pairwise similarity matrix. I can repeat that process with Bob and get another similarity matrix for him. And so the way people typically measure representational alignment in the literature is they compute some kind of distance metric or similarity metric on top of these two matrices. Right, so for example, we could compute the correlation between the responses we got from Alice and Bob. And what that would give us is a notion of how similar their representational geometry is of that set of objects, right, of these animal pictures. So let's walk through an example of what that actually looks in practice. Let's say I want to compare how humans and machines represent colors. First of all, how do we actually get the human representations? It turns out that cognitive scientists have had a trick for querying black boxes and getting representations out of them for about 80 years now. And that trick applied to humans, which was the original black box before machines, was to ask for these similarity judgments. And so what cognitive scientists would do is they would ask you, how similar are these two colors? They'd keep showing you these different pairs of colors. Assemble this similarity matrix here, and then apply a low-dimensional embedding method to try and find low-dimensional embeddings that respect the constraints laid out in that similarity matrix. Right, so if you, for example, told me that those two colors are really similar to each other, then I know that in some low-dimensional space of your representations, they should lie close together. It turns out when you collect that data from real people and you apply this low-dimensional embedding method called multidimensional scaling, MDS, what you get is the color wheel, right? So the color wheel isn't some strange artifact we invented to categorize colors. It actually reflects how people internally, mentally represent colors. Okay, but what about language models? Back when we started running some of these studies, this was around the same time everyone started studying LLMs when GPT-3 came out, and GPT-3 doesn't have any vision abilities, right? It's a text-only model. So how can you study its representations of colors? Well, it turns out you can just ask it about them in text, right? You can represent the colors as hex codes. You can represent them as RGB values, doesn't matter. You just need some way to be able to encode your stimulus as text. And so if you ask GPT this prompt, whatever, basically how similar are these two colors on a scale of 0 to 1, it'll tell you 0.3. So you can collect this matrix for GPT-3 of these color pairs. And when you apply multidimensional scaling to it, you get something that looks like this. Right? This is the sort of mental latent space of how GPT-3 thinks about colors. And it looks kind of familiar, right? It looks a little bit like the color wheel that we're used to seeing. So what we can then do is do a quantitative analysis of that, right? We can perform this study with humans with one set of colors, and with that same set of colors, perform the study with GPT-3 for whatever model. And when we compute the correlation between them, we'll get something that looks like this. So actually what we did in this particular paper is we looked at various psychophysical domains. We were looking at various domains that GPT doesn't actually have access to, things like sound, pitch, loudness, color, taste, things it's never experienced, doesn't actually, domains or modalities it doesn't have access to, but that it has heard about in text, to get an understanding of how does it represent these domains it has never experienced. And so what you find is that representational alignment between humans and models tends to be heterogeneous, right? It's not going to be homogeneous across all of the domains, as you're going to see pretty high variance between domains. So perhaps if you look at this chart here, one takeaway you might get from it is that when you're talking to GPT, you might be more willing or should be more willing to trust it to like color coordinate your outfit than you should be trusting it to design a recipe for you. Okay. Now, this is a really simple method, clearly, right? Like the reason I like starting with it is because it's something anyone can take and start doing research with immediately. You can, I started teaching this semester a few weeks ago, and we've already done an activity in class where I asked students to give similarity judgments over various pictures, or colors even. They can compare with each other to see how representationally aligned they are with each other. And then they can immediately query GPT and ask it the same thing and figure out, how aligned are they with GPT. But it turns out this really simple method is actually a very, very powerful and very deeply studied method, right? So if you dig enough through the literature, you'll find that this method is studied under various names in cognitive science, in neuroscience literature, in machine learning literature. It'll have names like representational similarity analysis, second order isomorphisms. It has, some relations to contrastive learning. In contrastive learning literature, you'll find it. It turns out it appears in all of these areas. Unfortunately, what we've been finding, has been the case over the past few years is that this research tends to be fairly fragmented. So all of these fields are rediscovering the same ideas. They're rediscovering the same methods. There's a lot of knowledge sharing. And so that's something we've been working on trying to improve, trying to create bridges between these communities, trying to define this subfield of representational alignment that actually has really interesting underlying mathematical problems, which I won't get into today, but that, would benefit all three of these communities if somebody were to make progress on them. So part of the goal of this talk is to get you excited about representational alignment, regardless of what background and which community you're coming from. All right. With that in mind, why do I think you should study representational alignment, in particular in this audience? So I'll say the first thing is that what we've been finding is that representational alignment seems to govern the communication dynamics between these various intelligent systems. And when I say intelligent systems, it turns out that can have a very, very broad definition. So you'll find studies that look at representational alignment between humans and animals, models, brains, right? So like neuroimaging. We have roboticists working with us who are studying representational alignment. You'll have sociologists and social psychologists studying representational alignment at the community level, right? Looking at different ethnocultural communities and how there's representational alignment between them, both within the communities and between different communities. Even at the level of different languages, how speakers of different languages are able to communicate with each other, how translation can work between those languages. And you can also look at it within the brain or within a machine. You can look at similarity judgments coming or representations coming from individual layers of a neural network. You can understand how aligned representations are at the beginning of a neural network with the representations at the end of a neural network. Right? Often what machines are doing or what our brains are doing is taking data and repeatedly re-representing it. So there's very interesting things you can discover by studying that, and it's a very widely applicable method. But in general, what it tells you about these systems is a lot about the dynamics of how they're able to communicate with each other, cooperate, and to compete. I won't get into that too much, but I'll say, the other sort of useful thing is that representational alignment also lets us predict the behavior of other systems. So generally speaking, if you can find a simple system that's representationally aligned with a complex or inaccessible system, so for example, if you can find a model that's representationally aligned with humans, then what you can do is predict human behavior or better understand human behavior by studying that simpler system. In particular, for today's audience, I'm going to focus on humans and models and students and teachers in particular. And the reason that representational alignment is particularly powerful when thinking about models interacting with humans is that we found it leads to all sorts of important downstream effects. So a lot of our work has been in this category here, machines learning from human teachers. And we found that if those machines are representationally aligned with their human teachers, right? If we're labeling data for these machines, if those machines think the way we do, it leads to better generalization, better sample efficiency. You can teach the machines with smaller data. It leads to things like robustness to adversarial examples, better interpretability, explainability. All of these desirable features that we want sort of naturally fall out of representational alignment. What we started working on recently is sort of over the past year is this idea of how representational alignment affects human learning from machine teachers. And the three questions I want to focus on today are these ones here. And what sort of started us thinking about this work initially was, I think, an experience that might be universal for everyone, which is that you meet a preeminent expert in a particular field. Maybe they're your professor, your mentor, your PI, and you are so excited to hear them explain their field to you, to learn from them. And then you can't understand anything they tell you, right? And it's not because the expert is being lazy and doesn't want to teach you. Oftentimes the expert would love to have everyone interested in their field, would love to get everyone upskilled in working with them, but they just can't teach you about it. And instead, you're better off going to your friend who's also sitting in the class, barely understanding what's going on, but understanding it slightly better than you are. And for some reason, your learning gain, your ability to learn the material is highly improved when talking to that peer as opposed to talking to the expert. So that's the question I'll start with first. The other two questions that we'll get to time depending is, in what ways should teachers and students actually be aligned? And finally, will it be enough to have a single aligned or student-centric AI teacher, or are we going to need personalized models for everyone? So let's start with the first question. Okay. We, in this particular study, posited that maybe there is sometimes a trade-off between expertise and representational alignment. Right? Maybe the expert knows the material really well, but they don't know you very well. They don't know how you think, and it's a struggle for them to figure out how you think. Your peer, meanwhile, maybe knows the material fairly poorly, but at least they know how you think. So, should our teachers be aligned, or should they be accurate if this trade-off exists? The absolute simplest study we've conducted, and we have sort of follow-up more complicated ones, but this one's the absolute simplest one, is where we said, okay, we're going to design an experiment where a teacher and a student observe a grid of objects. Here, we'll just color this grid for now. The teacher cannot see how the student observes that grid, how those objects are arranged in the student's grid, but it is the same set of objects. So there's some degree of misalignment between these two grids. We tell the teacher some kind of classification function over this grid, right? We'll tell the teacher, oh, this is category A, B, C, D. Now, the teacher's job is to teach the student to recognize those categories by giving the student labeled examples. So the teacher will say, okay, maybe this is a pretty reflective example of category A, I'll label that one. Maybe this one's a pretty reflective example of category D, I'll label that one. If the teacher is a very, a highly expert teacher, maybe they do this part correctly. Maybe they apply the labels correctly. But perhaps if we have a teacher who doesn't know the material as well, maybe they make mistakes sometimes. Maybe they'll accidentally mislabel this one as B, this one as C. All right, so what that actually looks like, and I think this is a little bit hard to see here, what this actually looks like in the interface for students is that they have this grid of objects. Here we have these little dinosaur drawings, and some of them have labels assigned to them. So you maybe can't see it, but it says A, B, C, D, so on. And what we ask the students to do now is to label the rest of the dinosaurs based on these training examples. All right. So what we vary in this experiment is the degree of representational misalignment between the teacher and the student. Right, so how distorted is this grid compared to this grid? And we vary the degree of teacher expertise. So roughly speaking, how many mistakes does the teacher make? First, we ran the study in simulation. We had, a large number of these teachers, a large number of students. What you're seeing here on the x-axis is the teacher error rate increasing to the right, and the student accuracy after learning increasing upwards. The colors here denote the degree of representational alignment between the teacher and the student. And what you might see that's pretty interesting is that sometimes, even if you increase the teacher error rate by 20%, right? So the teacher is mislabeling 20% of the training examples, you're still going to have better performance with a highly representationally aligned teacher than working with a teacher who has a 0 rate, is always correct, but is more representationally misaligned. We repeat that experiment with machines teaching real humans, and we find something that looks similar again to that. Right? So we see again that in many cases when teaching humans are better off learning from a teacher, even if it's a machine teacher, who is more representationally aligned with them, even if that alignment comes at the cost of expertise. All right. So, like maybe the takeaway we get from this is that we need models that think similarly to us, right? They need to take into account our individual differences. We see that there's a lot of different students on here. But we'll see how we can scale this up sort of into the real world a little bit. Right, so far we've seen that the way that teachers and students should be aligned at a minimum is over the subject material. That's essentially what this grid was getting at, and we've now been scaling up these experiments to algebra, to statistics, looking at notions of misalignment over basic concepts in those subjects and how they affect learning gain for students. But I'd argue that what we know from teaching classes is there's more to teaching than just the material. Right, as Alexis was talking about in her talk, we need to also be able to model the student, not just the material, but we also need to be able to model the student. So what does the student know? What are their skills? What are their misconceptions, etc. And so there's lots of exciting work on this, especially Alexis's beautiful work. One of the things we've written on it before is a study of how large language models perceive human decision-making, right? And we find that across a wide variety of state-of-the-art language models, they tend to overassume rationality in people, right? So if you ask them to try and model how people are going to be making decisions in sort of risky decision-making situations, or you ask them how people are making inferences when people need to make inferences about some kind of problem, the LLMs often, very, very often, assume humans are significantly more rational than they are. And so as a result, when you leverage those models to generate training examples for those humans, they're not going to be optimal, right? They're going to be relying on students extracting every bit of information from that training example correctly. But it turns out that that's not what students are doing. That's not how students are interpreting those training examples. And then, a third category that we want alignment over is actually the language we use, right? How we communicate with our students. We in our classrooms have students coming from various diverse backgrounds, from various diverse cultures, communicating, there's an increasing gap as we become older as teachers between how we talk and how we communicate and how the students in our classroom talk and communicate. And so, just giving you one example of that, we have a paper recently on looking at the representational alignment between humans and LLMs in terms of conversational tones. So we have humans and LLMs generate thousands of different sentences corresponding to different conversational tones. Then we have humans and LLMs rate all of those different sentences. And we find that, curiously, there's this interesting collapse that happens. So humans have this very fine-grained sense of different conversational tones. We can tell surprisal apart from excitement, apart from fear, apart from enjoyment, etc. With LLMs, there tends to be a bit of a modal collapse. So all of those emotions that I just described, most of them will be mapped into a single one that the LLM will think is excitement. And that goes both ways, right? So when the LLM is producing text for the human that it wants the person to interpret in a certain way, there's a communicative failure there as well. So this is another area where we're currently seeing misalignment between people and LLMs. And there's a number of other areas where we can look at, or where we should be looking at, the degree of alignment between humans and machines and these AI tutors. But I won't get into them today. I'll just say that, study this across many different domains. Everything you do as a trick as a teacher to try and better connect with your students, to try and get better results in your class, the LLMs, we need to test that in them as well. We need to figure out what's happening there. So let's say we figure it out. Let's say we have a teacher who is willing to do everything to figure out exactly what each student in their classroom is like, is able to adapt their language, is able to understand every student's misconceptions. Is that enough? Is this one generalist teacher, student-centric teacher, going to be enough? In the case where that teacher is interacting with a single student, that's great. That's going to work. The teacher, that's going to work out well. But as soon as we start moving towards classrooms where we have multiple students interacting with a single teacher, especially in the case where we have human teachers, right, who can't parallelize themselves to all of the students, who are time constrained, who have just a single lecture to relay all of the teaching material, what we start seeing is an effect that looks like this, right? As the classroom size increases, and this is back in our simulations from before, as the classroom size increases, even if we have a teacher who models all of the students in the class perfectly, and tries to tailor their teaching examples to all of the students simultaneously to optimize results for all of them. As the classroom size increases, or as the diversity in the classroom increases, the learning gain rapidly drops. And so our argument here is that a single student-centric teacher is not going to be enough. As we start scaling up our various AI tutor systems, as we stop thinking, purely in the dyad setting and start thinking about what's happening in entire classrooms or in entire schools, which is an experiment we're working on now, where we're trying to match teachers and students together based on these various parameters, we need to understand that our AI tutors are going to have to be tailored to the students. We can't deploy the AI tutors at the teacher level and just have it be a static model that does the same thing with all the students. We need to do personalization. So, since we're running out of time, I'll tie it up here. To summarize what we talked about today, right? So for effective teaching, teachers and tutors need to be well aligned with their students in several ways. We know this as pedagogues, but now we know this also in these machine teaching studies. The problem is that real students, human students, are diverse, and human teachers have limited time, limited resources. So we're going to need student-centric AI tutors that are individually aligned. And I'll make a perhaps bold claim that progress is going to come not from scaling up the next, to GPT-5, going from GPT-4 to GPT-5. Progress is actually going to come from studying human cognition, right? Doing studies like the one that Alexis showed us. That's where we're going to see progress. That's where we're going to see this increase in representational alignment. That's where we're going to see these individualized, personalized AI tutors. And so to finish off, if you're interested in representational alignment, we have this consortium working together of cognitive scientists, neuroscientists, machine learning researchers, roboticists from all over the place, all over the world, on defining this field of representational alignment. We have this preprint up, but if you have any ideas, if you ever want to discuss representational alignment, please get in touch. Happy to explore that further. I've got a quick shout out to all of the collaborators who participated in these various studies. Thank you.
Questions for you. Assemble the panelists up here. Have a little bit of a discussion of the time remaining. audience? Someone start with a question? So thinking about your students, adding fractions by adding numerators and denominators. One question you might ask such a student is, what's 3/4 minus 1/4? I think the students would immediately see a problem.
Wait, sorry, this is the student who's only doing the operation to the numerator? Or is it-
To the numerator,
To the numerator and denominator, oh, right, yes, yes.
so they'll see a little problem there, 2 divided by 0, and then might ask what's a half plus a half to try to get them on firm ground, and then try to explore how they're thinking about it. And I could see that going in many different ways. Maybe they have a visual representation of a half plus a half, maybe they have some algorithmic, and then I could see following that, and eventually trying to get the student, young person who could be not great class, but could get excited and discover something. Can an AI do that now? Is that something that you think the AI is moving towards? Yeah, just that kind of open-ended prompt.
Yeah, okay, this is a
That's
really.
for all of you, not just for, but go ahead.
I'll give a first step. I think this was a really great question and exciting question because, the model of teaching and learning that I presented was students sort of passively receives information. And the model, I think that you're suggesting is like asking questions that allow the student to have sort of that genuine insight on their own. I don't know off the top of my head if that's something, someone should study that. Like in a controlled setting, can language models ask those kinds of questions? My guess would be that they're not as good as they could be. Like, I don't think they're probably at the ceiling yet, given that it requires doing the sort of complex student modeling that, or modeling of student beliefs that we saw they struggled with in that setting. But I also think, going back to Ilya's point about progress being made on by studying human cognition, like we need to understand exactly how to model what's going on in the student's mind when they realize, oh, you can't have 0 as the denominator in the answer to a problem. And that was something that I remember I was like hitting my wall about with this project, is how do we what should the simulated students look like in this setting? And I think there's a lot more really rich modeling that can be done there that would open up teaching methods that can then simulate, okay, this is a good question to ask because the student will have sort of this like genuine insight on their own if I ask the question. So. Yeah.
So I can say maybe something thought connected to that. There's a beautiful study from France that came out this year. So far it was published at CogSci this summer, but I think they have like a journal paper coming up where they were studying how students in France represent fractions. So they had originally been studying fraction addition, fraction multiplication, fraction algebra, and they had a suspicion that the failures, like for students, the misconceptions were actually happening at an even more basic level. Students might not even be representing fractions correctly. And so what they tried to do is basically they asked students from all across France, something like 12,000 students, to put fractions on a number line. And they did this for students from grade, I believe, 4 to 10, something like that. And this wasn't complicated fractions. They had, it was like 1/2, 3/6, 6/3, these types of fractions. And they found that the error rate for students sort of in grade 4 to 6 was at around 80%. So 80% of the time they were putting fractions in the incorrect parts of the number line. And towards grade 10, that fell, but it only fell to about 50%. And so I think what that tells us, and like what that adds on to what Alexis is saying, is that like we really do need to understand what students are thinking and what students are doing, right? Like we can build this model that tries to model out the hypothesis space of what students are doing, but if we don't account for the fact that students might not even understand the fraction itself, we might miss that important misconception there. And so I think when we say we need to understand human cognition, right, I think we have to dig fairly deep, right? We can't risk making assumptions as experts that everyone else is thinking about the world the same way we do, even its very basic assumptions.
And that's an example where if all you were doing was asking text questions of the students, you might never reveal that misconception that involves actually drawing it out on the number line. I'm curious, in your system, in the PS2 PAL, are there interactions that are ever visual or using diagrams, or is everything text and algebra based?
Yeah, so I think this is a place where having the many years of feedback was very helpful, because I knew the diagrams that we would draw as our answers. And then I put obviously a text linked to the image that displays. And so, but in this semester, implementing it, this is one of the biggest comments that we're getting from students, which is, they're learning about forces. And they say, like, I wish it would give me those forces. And it tries with, ASCII or whatever, but it's not quite there. So yeah, the representation isn't quite there. But when you know what the students are gonna ask, we put it in.
You have a few canned diagrams of
There you
what you think the misconception makes diagrams of TIC-C.
Yeah, exactly.
The point about the need to understand how people think. I'm guessing that in this case in France, it was a human being came up with the idea, let's make sure they understand fractions, right? And this seems, I'm sure if we have teachers, they will have, but in general, do you think of using machines to identify that? Or are we always going to rely on teachers with experience?
Yeah, so I think, like I've seen some studies, and we're starting to explore this as well, trying to create these graphs of sort of skill dependencies, right? Like what does a student need in order to be able to solve a probability problem? And what we're trying to do is see if we can automate that process, right? So we could go to experts, we could go to teachers, and we can ask them like, oh, and what does a student need to know to be able to understand Bayes' rule? And they say, oh, like conditional probability and probability. And it's like, oh, what do you need to be able to understand like probability and conditional probability? And we'll say, oh, well, maybe you need to understand like addition of fractions, and you need to be able to understand, whatever, something else. And if you prompt them enough times, an expert, you'll be able to build out that graph. We suspect that if you prompt sufficiently powerful LLMs enough, you'll be able to build out large portions of that graph as well. What we're seeing so far is you probably need some expert intervention, like at this stage at least. Maybe in the future, the amount of intervention you need decreases, but that's sort of where we're at right now, I think.
How do you know when to intervene? So I was talking to someone involved with their companies building AIs that solve math Olympiad problems. And some of them are feeding those into a proof checker, and that's how they're verifying. How do you know in these models, whether it be the tutor that's telling that, or the student might be telling something, or there when you build out that graph? How do you know when you need verification? Or how do you verify what the machine is telling?
Yeah, I don't know if you want to. I mean, at least for the graph case, like maybe I'll start at a different point. In general, one of the things we evangelize, and we have a sort of position paper coming out in a few days on this in NHP about it, is that like when we design AI systems for people to work with, we should start moving away from this paradigm we've had so far, which is that AI systems should replace people, like they should automate away a task. And increasingly, we're getting to the point where we should start thinking of AI systems as being potential thought partners for humans, right? So some kind of system that we're able to interact with, that augments us, that helps us out, that both understands us and we're able to understand and communicate with and create something better together. And so when it comes to this graph creation task, for example, what we're looking at is, at what points should you be surfacing the graph to people? You know, can you get a measure of the uncertainty of the agent of the LLM as it's building up this graph? Is that going to be a good signal for when you should get expert intervention? Is it okay to like ask the expert to look at it more often, even though that's going to sort of cost more in terms of human labor? So, you know, a lot of it is balancing those trade-offs. You could just ask an expert to intervene all the time, but that wouldn't be, you know, that wouldn't be great either. But I do wonder what you're seeing in your cases, right? The sort of the PAL system, the PS2 system.
For example, like how much do we actually need? I think so one of the things that we made sure to do was choose topics that students hadn't seen before.
You mean for the study?
For the study, yeah.
Yeah.
Yeah, so I think that we would probably need more expert intervention to verify that it's getting it right. If it wasn't something that was so straightforward. Also, this semester, you know, I think that like introductory physics is one where you the models have been shown to be so accurate that it's not too much of an issue. But I think that you get to more advanced topics, like trying to solve the traveling salesman problem, having some expertise or some context that doesn't have as helpful.
On that one, I think I just got lucky in the cities that I picked. The naive nearest neighbor algorithm got the wrong answer. I had planned that, but that was helpful. It's bad responses.
In the absence of audience questions, I'll ask one final one for each of you to speculate in whatever order you choose. About how you envision, whether it be the classroom of the future or maybe the undergraduate or high school or elementary school experience, whether that's a mix of classroom and at-home learning. Is there some vision you have in your mind of how that will be or should be or working toward, say, on a 10-year time scale? You speculate.
Since I'm sitting closest.
All right, great, go ahead.
Well, I think that the one thing that I thought about doing this a lot was where do we want students to be moving at their own pace, and how can we get them to a place where when they're interacting with each other, it's most effective. So I think that's one question that'll tell us a lot about what we want the classroom to be, because the classroom is often interacting with other people. So if we want the student to say be working on a project on a particular topic, we need to make sure that they're at a place where they can effectively work on it and communicate with each other, maybe have the same representations as each other. And so I think that there's probably a lot more that the students will do in getting up to speed in the language and the topics on their own. And then when they get to the classroom, I mean, there's no reason that they wouldn't also want to have an AI involved in the teaching. Your AI teaching buddy that helps you teach the students, or it helps get the students to all work better as a group. It's, you know, it says that person didn't speak, and it's, you know, paying attention to all the students in the room, and trying to make sure that they're all involved. But it should be basically using the systems to make our communications better when we are together.
I guess we'll go. I had a student in the gen ed class who said, you know, well, I was originally thinking I would go to law school, but now that I've taken this class, I'm not sure there's going to be careers for lawyers in the future. Which was an interesting remark. But I don't think actually these are going to replace humans. In part because I suspect that by the time we get human level performance, that's going to cost as much as humans in terms of energy cost and chip cost and many other cases. I think it's gonna be a very long time before we have robots that are as capable as humans in terms of dealing with the physical world. So those of us who rely on cognitive labor, we may be in for a bit of a come down here. But I think this point about social interaction, I'd love to find ways to sort of leverage the AI to increase social interaction and increase the productivity of this social interaction. I can imagine, you know, if the AI can do tasks that we would have found, you know, tedious in a collaboration, then we can, you know, humans can have a lot more fun in that collaboration and focus on the higher order tasks.
Yeah, I agree with what's been said, and maybe to add on about the social piece, like I think, you know, I've heard described this like vision of interacting with language models where you're basically using language almost as like a programming language to, you know, you're programming in English to elicit certain kinds of outputs from a language model. I think like that's a really interesting way of thinking about how the role that LLMs might play in education is. Maybe, I think this touches on what you were talking about in your talk, is like thinking about how do we get students to improve on these like metacognitive skills to be able to work with systems that are doing the tedious thinking in a more systematic and creative way. And I think it's not super clear to me exactly what that's gonna look like, but I think it's really exciting. I also think, I mean, this is just another sort of area that we haven't talked about that I guess Logan mentioned in his talk, that I think could be an exciting place for change, is thinking about better tailored evaluation. So not having, you know, I think I personally, just my own opinion, think it's helpful to have sort of general standards of, okay, by, you know, let's try to get students understanding these kinds of concepts at this point in schooling, but have that journey be more tailored to students, and rather than having maybe like one standard test that everyone takes, have it be sort of this growth-based thing where you're looking at how much should they improve and can tailor the way you're evaluating students to the way they think and what their goals are and things like that. And I think language models can help us do that sort of tailored evaluation eventually.
Yeah, I mean, I really agree with that. I agree with what's been said before. I think it like takes us back to what Logan initially said the challenge is, and I agree that is the challenge, which is like what should students learn, right? Like 5 years from now, maybe 10 years from now, we're going to get to a point where everyone has a personalized tutor. It's the latest AI model. It works so well. We can tailor their experience completely to them. Maybe we can have individual evaluations that are like, you know, allowing individual progression, monitoring learning gains separately for each student, other than doing standardized tests. But the question is like, what are we driving the students towards? What is the objective that we'd like to achieve? And I don't know. I think that's a difficult question. It's a difficult question, first of all, because, you know, there's sort of half of the AI community telling us that like work is going to be irrelevant on that timeline 5 to 10 years from now. So what should all of us in general be doing then? But even more pragmatically looking at it, you know, there is also a question of like, should we personalize education to that degree? Should we give everybody their own tutor? There's this argument that comes from the kind of like emergent communication literature, the information theoretic communication literature, that says that like, actually, part of the point of schooling is creating this sort of shared basis, right? Something that enables and improves communication between an entire generation, maybe even multiple generations of people growing up in the same community. It enables them to communicate more efficiently, to cooperate better, to build things together on top of that shared basis. And so, you know, I in my talk was talking about like personalized AI tutors, but there's a risk that comes from that we're going to lose that shared basis potentially. So I don't know. I think that's maybe that's the open challenge to leave to everyone, which is what should we be teaching students in the future as we have increased resources to be able to teach them anything essentially. Yeah.
But the thing I would say is that if you have learned anything since 2020, is that plugging people to a computer doesn't work all day long for students, right? It's not good for their social interactions, it's not good for their happiness. So that much, so there needs to be, I think that's what I was saying, but there needs to be social interaction. I think we all thrive on that, and that's part of it. And the other one, I mean, it's like having a children, and how much do you feed? I think depends on how eager each person is to learn. I mean, I don't think it's up to us to put the boundaries. I think it's up to the person. Parent is boundary. And my 5 cents.
Thank you. Well, with that 5 cents, I think we've come to the end. So let me thank Mike Douglas for co-organizing this session, and in fact, the whole lead organizer for the whole program. Thank all the panelists for their wonderful, stimulating talks and thoughts. Thank you.